The most important eigenvalue equation that we have in quantum mechanics is the Schrodinger equation. If we go back to our h psi equals E psi Schrodinger equation, we see that this is an eigenvalue equation. Our operator is H, or the Hamiltonian operator is what we call it. And our eigenfunctions are going to be what we call the wave function, our psi functions. And we're generally going to be looking for eigenfunctions of the Hamiltonian operator. And then our energies are the eigenvalues. And so this is the, our most important equation in quantum mechanics is an eigenvalue, eigenfunction equation. So let's take a look at our Hamiltonian operator and what exactly is it and what does it represent. So Hamiltonian, again, I'll write it out again, negative h bar squared over 2m, second derivative with respect to x, plus potential energy. The Hamiltonian operator represents the total energy of our system. And so our energy can be composed of two types of energy. We have kinetic energy, the energy of motion, and potential energy. And so the potential energy is explicitly given right here. And this term on the left, this represents the kinetic energy of our system. Now, this doesn't look like our usual way of representing kinetic energy, right? If we're looking at classical mechanics, kinetic energy is 1/2 mv squared. All right, that's our usual definition of kinetic energy for classical mechanics. But in quantum mechanics, our kinetic energy looks a little different. So we can actually show how these are related by using the quantum momentum operator that we introduced in the last video. So we can actually rewrite this if we remember that momentum P is equal to mass times velocity. We can say, well, kinetic energy, we can rewrite it as P squared over 2m. Now these two are the same. They're just different ways of writing the same equation. Let's take that version of the kinetic energy for a classical system and substitute the quantum momentum operator in there. All right, so kinetic energy will be equal to the momentum operator. Again, we'll look at just one dimension, but this can be applied to multiple dimensions. So we'll just look for x squared over 2m. Now, we have an operator and we squared it. What does that mean? A squared operator, so if we have, say, a hat squared f of x, this is just the same as doing the operator twice. So do a twice on f of x. So that means we just need to put two copies of our momentum operator here on the top. Okay, and so if we're looking at, so we have some constants here, and we have two derivatives. So that'll just be a second derivative. So we'll have second derivative with respect to x. Our 2m is just going to be hanging out on the bottom here. And we have a negative times I squared with another negative. So there's two negatives and an h bar squared. So overall, we'll have I squared is -1. We have negative, negative, negative. We have three negatives. That ends up being overall negative. And so we end up with negative h bar squared over 2m, second derivative with respect to x. And so we can see when we use the momentum operator that's true for quantum mechanics, we get that this is the kinetic energy. It follows the same formula that we have for classical mechanics. And so what the Hamiltonian represents is it's an operator that represents both the kinetic energy and potential energy of the system. And that our kinetic energy is given by this negative h bar squared over 2m. Okay, so now that we've set up our Hamiltonian, right? What is a Hamiltonian operator? The Schrodinger equation is this eigenvalue equation that we're trying to find eigenvalues and eigenfunctions. Let's go ahead and apply this to an actual system, to the particle in a box. And so in the next video, we'll set up what is the particle in a box.